What's up guys, it's Simon Fiaz and today's video is on AQA AS Level Chemistry June 2023 paper 1. Question 1.1 gives the full electron configuration of the element in period 3 with the highest first ionization energy. Period 3 with the highest first ionization energy. 1s2, 2s2, 2p6, 3s2, 3p6. How many electrons are 2, 4, that's 6, plus 6, 12, 22 electrons. So 1s2, 2s2, 2p6. No, it's not 22. 2 plus 2 is 4, 4 plus 6 is 10. 20 electrons, and yeah, that makes sense, calcium. So 1s2, 2s2, 2p6, 3s2. Because once you go further than that, further than calcium, it's going to be electrons going to be in another outer shell, so it's going to be more shielding. And the thing about potassium was it was 1 electron less, so it would be 3s1, highest first ionization energy, so 3s2 would be better. 1s2, 2s2, 2p6. Oh, I completely forgot the 3p6. So 1s2, 2s2, 2p6, 3s2, 3p6. So it's actually going to be argon then here, because 4 plus 6, 10, 18. Okay, given the equation, you state symbols represent the process that occurs when the second ionization of sodium is measured. So Na plus gaseous plus, no, Na2 plus gaseous plus E minus, and then Na plus gaseous here. Perfect. Identify the period 3 element. So what you would have to do in this case is alhamdulillah, is you'd have to look at the ionization energies and look where's the massive jump. So the massive jump is from here to here. So the period 3 element and how many electrons has it got? The massive jump is when the outer electron is removed from the 6th outer shell. So the period 3 element then it's going to be sulfur. Because if we draw out the structure of sulfur, 16 electrons, S2, 2s2, 2p6, 3s2, 3p6, 16. How's that enough? 4, 10, 12, 18, that's fine. When there's 6 electrons be removed, 1s2, 2s2, 2p2, and yeah, it's going to be sulfur, Y, and then this bit, because large jump after 6 electrons moved. Large jump after the 6th electron is removed. Due to 7th electron removed. Electron being removed, and then we would say electron removed from the 2p orbital. Electron being, and you have to be very specific, don't say being removed from p orbital. Which p orbital? The 2p orbital, hence less shielding, that's closer to the nucleus. Describe the structure and bonding in magnesium. Okay, so what is magnesium? Magnesium is obviously going to be, it's a metal. So that's what I would talk about really. And if you look at the Mott scheme, that's what it's talking about. Giant lattice of the Mg2 plus cations, electrostatic attraction between the positively charged ion and a delocalized electron. So, but in this case, very specific to the question. You can't just say giant lattice of Mg2 plus, well, cations because it's positively charged ions, and therefore strong electrostatic forces of attraction between Mg2 plus ions and delocalized electrons. The giant lattice Mg2 plus ions, electrostatic attraction between 2 plus ions and delocalized electrons. Yeah, I just said strong electrostatic forces of attraction. I always like to say that. But yeah, giant lattice Mg2 plus cations, electrostatic forces of attraction between Mg2 plus ions and delocalized electrons. Extend the trend of atomic radius elements down group 2 from magnesium to barium. Magnesium to barium. I'm going down the group, and what happens to the trend of atomic radius? It's going to increase then. Clearly going to increase. Increases, the number of energy levels increases. Yeah, the number of electron shells increases is probably best. Yeah, number of electron shells increases. Of electron shells increases. Given the equation including state symbols for the reaction magnesium with steam. So magnesium with steam, including state symbols, so Mg solid. Because it's steam, the H2O is going to be gaseous, and I'm going to form magnesium oxide plus hydrogen gas, and the magnesium oxide is going to be solid. That's just how well you know your equations. You either know what you don't. There you go. Mg solid plus H2O gaseous from MgO solid plus H2 gaseous. The observations: bright light, white, bright light, white. The thing about these equation questions is they like to often repeat them. So memorizing these, well, you should already memorize the equations, but memorizing equations from past paper questions, definitely do that. 2.4 state the formula of the least soluble of the sulfates, least soluble magnesium to barium. So it's going to be the barium sulfate, BaSO4. Say give a use of this, barium meals. Yeah, X-rays. Remember, barium sulfate used in barium meals. It's 2.5 a sample of strontium is made up of only 3 isotopes, 86SR, 87SR, and 88SR. This sample contains this much of 88SR by mass. Sample of strontium has AR that. Calculate percentage abundance of each of the other 2 isotopes in the sample. 4 marks. And really, yeah, the first calculation question on this paper. And how many questions are here in this paper? yeah, this video is only in section A. So only 8 questions, and only got to question 2, and now the math calculation questions are getting involved. So first thing I would do is construct it. I know AR is 87.73. I know 83% by mass of 88 SR plus 86 plus something 86 and something 87 divided by 100 is a percentage abundance. So if I say that if I let 87 SR equal X, right, then what I would say is then plus plus X plus 86 bracket 100 minus 88, which is what? Because no, 100 minus 83, which is 17, and then therefore 17 minus X. Hopefully you got it right. Let that equal X. 86 times by 17 minus X, so 0.17 minus X, yes. And if abundance of 87 SR is X, then yeah, it's going to be 87 times by X, which is what I forgot to do. So 87X. Then you times by 100, then you get 8773 equals, and I need my calculator. The hardest part for these type of questions where it's involving algebra and it's like really basic stuff, but because a lot of students, including myself, haven't practiced these type of questions, it becomes very, very difficult in exam time pressure. So 83 times by 88, 7304. 7304 plus 87x, 86 times by 17 plus 1462 minus the 86x. Then what happens is then I collect the like terms, plus 1462, move it to the other side, 8773 minus my answer, and then I get 87 minus 86x. What's that? That's going to be x equals 7. So the percentage abundance of 87 SR is 7%, and the percentage abundance of 86 SR, well, what's it going to be? It's going to be, well, if I know this is 83, this is 7, well, the 83 plus 7 is 90, this has got to be 10. Perfect. And yeah, don't forget the percentage. Hardest part, constructing the equation. Let 87 SR equal X, so 87X, and then 86 bracket 100 minus this, minus that, and that's it. Question 2.6. Magnesium hydroxide is used as an antacid to treat indigestion. A student does an experiment to determine the percentage by mass of magnesium hydroxide in the indigestion tablet. For this much of HCl added to this much of powder tablet, all the mixture is swirled thoroughly. All the magnesium hydroxide reacts to HCl as shown. Might HCl remaining after the reaction determined by the titration with this much of sodium hydroxide. This much of sodium hydroxide is needed. Calculate percentage by mass of magnesium hydroxide in the indigestion tablet. So I'm not really fully sure what I'm doing, but I know for a fact I'm gonna have to find out moles. So that's what I'm gonna do first. Show my working out, concentration times volume. And what do I get? 40 divided by 1000 times by 0.200, 8 times by 10 to the power minus 3 moles. Then what I need to do is then be like, okay, now what else can I find out? Well, I can find out the number of moles of this. Which is going to be 29.25 divided by 1000 times by 0.100. 2.925 times by 10 to the power minus 3. Then, so I've got the moles of this worked out. I've got the moles of this worked out. Okay, so I want to find the percentage by abundance of that. I've got the moles of HCl, I've got the moles of HCl remaining is by titration with this. Magnesium hydroxide. So I need to find out the moles of HCl. The moles of HCl. The amount of HCl remaining is determined by titration with that. So what I need to do then is I need to find out the moles of HCl remaining, which is just going to be then 8 times by 10 to the power minus 3 minus 2.925 times by 10 to the power minus 3. Then what do I get? I'm going to include brackets around it. 8 times by 10 to the power minus 3 minus 2.925 times 10 to the power minus 3. 5.075 times by 10 to the power minus 3. 5.075 times by 10 to the power minus 3. And that's the number of moles of HCl remaining, right? Then what I need to do is, I don't know, I've got 1 to 2 molar ratio. So then I divide that by 2. If I just press divide by 2, 2.5375 times by 10 to the power minus 3. And that is the moles of magnesium hydroxide. Then I need to use Moles' mass over MR to find out the mass. Moles mass over MR, so therefore the mass is going to be the number of moles, 2.5375 times by 10 to the power minus 3 times by the MR of magnesium hydroxide, which MR of magnesium 24.3 plus 16 plus 16 plus 2. So I do my answer times by 24.3 plus 16 plus 16 plus 2. Then I get 0.147 something. And I'm going to do that, the actual yield, over the theoretical yield. So my answer divided by 0.200 times by 100. And I get 74%. And that is perfectly the correct answer. So find out the moles of HCl, find out the moles of sodium hydroxide, find out the moles of HCl reactive magnesium hydroxide, amount of HCl remaining, the amount of HCl reactive with this, so that minus that, then the number of moles of magnesium hydroxide, then the mass, and the percentage by mass. Exactly how I did it. And yeah. And question 3, suggest 3 improvements to this method. So this is one really. So first things first, record all masses. Record all masses. Invert the flask several times. Record all masses to 2 decimal places. Accurately to 2 decimal places. Invert the flask several times. And what's another one? Ensure the bottom of the meniscus is on the graduation mark. Ensure the bottom of the meniscus is on the graduation mark by using a dropper when close to the graduated mark. graduation mark. Then it says different student uses the correct method to prepare this much in a volumetric flask. Uncertainty is that calculate percentage of uncertainty in the volume of sodium carbonate solution. So student different should use the correct method to prepare this much volumetric flask. So then it's just going to be 0.20 divided by 250 times by 100. Perfect. 0.080%. 0.080%. Question 4. Determine the MR of M. Identify M. M is a group 2 metal that forms a nitrate that this much of M is heat strongly decomposes completely. The mixture of the gases formed has a volume of that. Identify, determine the MR, identify M. So immediately I'm thinking ideal gas equation, and I want to find out the MR of something, so I'm going to use moles. But this question, it is that simple, but there's subtle tricks to it that you need to be careful for. So I find the number of moles, pressure in pascals, already in pascals, times by volume 225 in meters cubed times by 10 to the power minus 6 divided by 8.31 times by temperature in Kelvin, so 450 plus 273. Now what would that give me? Number of moles of gas, the mixture of gases formed, right? Determine the MR of N. So if I put that in a calculator, so 101,000 times by 225 times by 10 to the power minus 6 divided by 8.31 times by 450 plus 273, and I get the moles as N equals 3.7823748882 times by 10 to the power minus 3. And now this part is where most students go wrong, including myself. I think this was on the mock like last year or something, and I got it completely wrong because it says the mixture of gases formed. Is that a gas? That's a solid. So the number of moles of gas formed is 5. This, I want to find the MR of this, so it's a 2 to 5 molar ratio, not a 2 to 7 molar ratio. If you do 2 to 7 molar ratio, you get everything wrong. You get the MR wrong because you got the wrong number of moles, and then the identity of M, you get that wrong as well. 2 to 5 molar ratio. So then I divide these moles by 5 times by 2, and then I get N equals 1.51 times by 10 to the power minus 3, round to 2 decimal places. I want to determine the MR of N, NO3. So moles is mass over MR. Moles mass over MR. MR is mass 0.320 over the number of moles. So 0.32 over the number of moles. And then I get the MR as 211.5. I'll put in brackets 212. Identity of M. Well, if the total MR now is 212, then I need to do 212 minus, well, what do I have again? Here, I need to get rid of this. Nitrogen, which is 14. Yeah, that's the MR of nitrogen. Minus 14 plus 14 plus 16 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 plus 16. Then I get the MR as 88. So MR is 88. And then I just look for the element with the MR of 88. which is radium. So radium Ra 211.5 bracket 212. 211.9. Allow 211.5 to 212, so perfect and perfectly fine. The MR 87.9, so strontium. Well, I got 88, so I got. Oh, I forgot. MR is the top number. How could I forget that? But even if I got that, then yeah, 88. So then I would get strontium then, not radium, strontium. Just silly mistake. I thought MR was bottom number. It's always going to be the top number. So yeah, strontium, I would get that as well. So SR. And 5 marks for that. Question 5, discuss the difference between shapes of CF4 and XCF4. Beautiful question if you really are confident with the shapes of each molecule. So I already know XCF4 is square planar, CF4 is it trigonopyramidal, a tetrahedral. So the shapes CF4 equals tetrahedral, XCF4 equals square planar. And that's it for your stage 1. Just state the shapes. Stage 2, explaining the shape of each molecule. Well, 4 bonding pairs, 0 lone pairs in CF4. 4 bonding pairs, no lone pairs. The electron pairs repel each other to be as far apart as possible. Electron pairs repel each other to be as far apart as possible. / electron pairs repel each other equally, and then therefore bond angle is 109.5 degrees. Stage 3, like this is a really nice question to put for, you know, a shapes molecule bond angle question, because it's not just testing your knowledge on shapes, it's testing your knowledge, explaining it, comparing it, and explaining the bond angle as well. And that's really it for this topic of bond angles and all that, shapes of molecule. So XCF4, it's got 4 bonding pairs, 2 lone pairs, and what do I know? Bond angle is 90 degrees. Bond angle is 90 degrees. I already knew that off by heart. But then you say lone pairs repel to be as far apart as possible. But they also repel more than bonding pairs, and lone pairs repel to be as far apart as possible. Explain about the electronegativity of the halogens decreases down the group. Larger atoms, larger atoms, hence more electron shells. More electron shells, weaker attraction between nucleus and bonding pairs of electrons. Weaker attraction between nucleus and bonding pairs of electrons. 6.2, state one similarity and one difference between these reactions. Concentrated sulfuric acid reacts with solid sodium chloride and solid sodium bromide. One similarity. Well, one similarity is that they both form hydrogen halides. They form hydrogen halides. And then the difference is just how well you know these equations. Well, if you do know them quite well, you know bromine. You could also say that sulfur dioxide produced with bromide, or just say bromine undergoes a redox reaction. That's probably the most common one. Bromine undergoes a redox reaction. Because remember, with the reaction between concentrated ferric acid and solid sodium bromide, there's two equations. Whereas concentrated ferric acid and solid sodium chloride, it just ends at the first equation. Similarity, they both form hydrogen halides. And the difference, bromine undergoes a redox reaction, and you could also say that, whereas chlorine does not. Give a half equation to show the oxidation of iodine. So iodine is I minus, and I'm going to iodine. I need a 2 here, and I need a 2 here. Equation reduction of concentrated ferric acid, H2SO4, to hydrogen sulfide, and you need to know the formula of it, obviously, which is H2S. Well, I've got 4 oxygens on the left hand side, so I need to add 4 H2Os on the right hand side. But now I've got 8 H pluses, so I need to add 8 H pluses. But now I've got an overall charge of 8 or plus 8 on the left hand side, so I need to add 8 negatively charged electrons. And now if I compare it, 2 hydrogens, 1 sulfur, 1 sulfur, 4 oxygens, 4 oxygens, 8 hydrogens, 8 hydrogens, overall charge neutral. Then use your half equation to produce an overall equation for this reaction. Well, I look here, I've got 2 negatively charged electrons. Here I've got 8. So I'm going to times this first equation by 4. So I get 8I minus 4I2 plus 8E minus. Negatively charged electrons cancel out. And then I've got 8I minus, add the two equations, half equations together, plus 8H plus H2SO4 arrow 4I2 plus H2S plus 4H12. 8I minus, so 2I minus arrow I2 plus 2E minus, 8E minus plus H plus H2S4 H2S plus 4H2O, 8I minus plus H plus H2SO4 arrow 4I2 plus H2S plus 4H2O. Perfect. These type of questions, half equations, more practice you do, the better you get at it. Then it says compound X is dissolved in a polar volatile solvent, is ionized by electron spray ionization. Each ion is accelerated, so that is the kinetic energy of that. Kinetic energy is given by the equation that time of flight along this long flight tube is that determine the mass of 1 mole of X. That's what all it wants. So what I'm going to have to do is find out the mass in kilograms, then convert into grams, and then I want a mass in 1 gram of 1 mole, then times by Avogadro's constant. Yes, so rearrange the equation, times by 2 divided by that, so I get m equals 2ke divided by v squared. And I know velocity is distance divided by time. The distance, let me just double check. Yeah, so distance is 0.750. The time is 2.48 times by 10 to the power minus 5. Find out the velocity and then substitute into here, squared. And 2 times by kinetic energy, which is 1.36 times by 10 to the power minus 16 in joules, divided by the velocity, almost right answer from my calculator, squared. And that give you the mass in what? Mass in kilograms. So, first thing I would do, 0.750 divided by 2.48 times by 10 to the power minus 5. Keep that in my calculator. Then I'm going to do 2 times by 1.36 times by 10 to the power minus 14 times by 10 to the power minus 16 divided by my answer squared. I get the mass in kilograms, but I want the mass in grams. So how do I go from kilograms to grams? I'm going to divide by 1,000. So I'm going to divide my answer by 1,000. So I get 2.97 times by 10 to the power minus 28. So 2.97 times by 10 to the power minus 28. And then I times by Avogadro's constant. So let's double check that. Perfect. So velocity is that, substitute that in, then oh, I'm not going for, oh my days, I'm so dumb. I'm going from grams to kilogram. I'm going from, no, I'm going from kilograms to grams. Kilograms to grams, I divide by 1,000. No, I don't. I times by 1,000. Yeah, I just can't believe I got that wrong. So then, yeah. So it'd be 2.97 times by, well, times by 10 to the power minus 22 then. Yeah. And then I times by 1,000. 2.97 times by 10 to the power minus 2. That's already times by 1,000. That's in grams. And then times by Avogadro's constant. And I get 178.9. But the mass of 1 mole ionized by electrospray ionization. So then I need to do that minus 1. So then I get 100 and yeah, subtract 1. Get 179. Well, I should have got 0.1 and then subtract 1 because electrospray says in the question electrospray ionization, and then I get 178.1. So find out you get a mass in kilograms, from kilograms to grams. I times by 1,000 and then subtract 1. Set the meaning of the term electron impact ionization. High energy electrons from electron gun. High energy electrons from an electron gun are used to knock out an electron from each molecule. To knock out an electron from each molecule. High energy electrons from an electron gun are used to knock out the electron from each molecule. Identify the ion formed from this mixture which the detector last. So we've got argon, carbon dioxide, nitrogen, oxygen that reaches the detector last is going to be the one, the one with the highest MR. So it's going to be carbon dioxide because of ion positive charge. Perfect. Has the highest mass to charge ratio. Has the highest mass to charge ratio, hence will travel the slowest. So how the ions are detected. The ions are detected by gaining electrons. How abundance is measured, proportional to the size of current. Yeah, proportional to the size of current, that's fine, but I need to be a bit more specific. Hit a detector and each ion gains an electron. So ions hit a detector and each ions hit a detector and each ion gains an electron, generating a current. And then how abundance measured? Abundance is proportional to the size of the current. Perfect. Question 8. Solution containing this much equilibrium, determine the amount of moles A and B in this equilibrium is a mixture at equilibrium. So I'm just going to use the ICE method. We're not going to have to use algebra. Like with these questions, you can spot when you need to use algebra or not. In this case, I'm not going to need to use it because I'm already given equilibrium moles or something. So initially, I've got 0.6 moles of this. I just solution containing this much moles of B. Amount of C is 0 because I've got equilibrium moles of 0.28. So I'm adding 0.28. And in this case, I'm going to minus 0.28. And in this case, I'm going to minus 0.28 times by 2 because it's a 2 to 1 mole ratio. So 0.60 minus 0.28, 0.32. If this method doesn't work for you guys, that's perfectly fine. Just find a method that does work for you and keep looking for one. Watch YouTube videos, ask your teacher, and then once you've got a method that works for you, perfect. Then just stick to that. And then keep practicing it, and eventually you'll become very confident with it and do it very quickly. So KC square bracket, so it's going to be the products. So C in square brackets over the reactants A and then B. Because I've got 2 moles of B, it's going to be squared. Predict the effect in any value of Kc temperature is decreased. Well, I know the forward reaction is exothermic because delta H is negative. If the temperature is decreased, equilibrium shifts to the right hand side exothermic direction to increase temperature. So I'll have more products over the same amount of reactants. So Kc would actually increase. So first prediction increases. Kc increases, and now I need to just say what I said. So equilibrium, as temperature is decreased, well, first things first, forward direction / reaction is exothermic, so equilibrium shifts to the right hand side / forward direction / exothermic direction to oppose the decrease in temperature, hence increasing temperature. 0.32, 0.04, perfect. Kc increases, equilibrium shifts in the exothermic direction to oppose the decrease in temperature, to increase temperature. Question 8.4, calculate B at equilibrium. So I've got my Kc expression. I want to find B. So first thing I would do is rearrange it. So time by that, B equals concentration of C divided by concentration of A times by Kc, and that's going to equal to B squared, but I want B, so it's just going to be the square root of that. And I know concentration of C is 0.62 over A, which is 0.48, times by 7.8. Square root of 0.62, 0.48 times by 7.8, 0.47. Oh, did it say to appropriate number of figures, so then I wouldn't get the final mark, which is a shame. So therefore 0.41. I didn't read the question properly, but yeah, very simple though. Rearrange it, substitute values in, you get B, but then remember to give it to 2 significant figures. And that is the end of section 8.